The second derivative test. Okay, so what do we gotta do first? Take the derivative. Okay, but maybe before we do that, yeah, what's the domain gonna be? Okay, so let's, this is kind of a pre-calc issue, probably more than anything, finding domains. So maybe it's a little bit of good review here. You're looking for any parts of any function in this composition of functions. F of x is a composition of a whole bunch of stuff, right? We're trying to look for any part of any function that's going to cause problems, right? Well, the x squareds are fine, right? There's no issue there. But what about the log x? What's the domain of log x? Think what a log function is. It's going to be, no, it's not all reals.
Isn't it all positive?
Positive reals, yeah, right. So it's got to be positive numbers. So we know then that the domain is going to be
Here.
0 to infinity. Good. And you see why we want to do that right away, because that's going to impact what our table looks like. And we only have to look for positive values in our table. Okay, so now we want to differentiate. So we got our domain, f prime of x. So we're going to have, we're going to have to differentiate term by term. I've got two terms, so I'll just differentiate, one at a time. First one, how am I going to have to differentiate the first one? Product rule. Okay, so we're going to have negative 2x squared times the derivative of log x, which is what?
1 over x.
1 over x. There you go. Okay, plus log x times the derivative of negative 2x squared, which is what? Plus the derivative of 19x squared. What's that? 38x. Okay, so there's our first derivative. Let's clean that up a little bit. We could cancel an x here. Right, so that's going to give us negative 2x plus 38x is 36x. Everybody agree? And then here I'm just going to have a minus 4x log x. Okay?
Wait. Oh, right. I see that.
Okay, so if I draw a little line, so these two terms combine. Okay. So what do we need to do with our first derivative? Find the zeros. And is there any place where our first derivative is undefined in our domain? No. We agree the only place where our first derivative is undefined would be for non-positive values of x, but those aren't in our domain, so we're fine. So then we're just looking for zeros of the first derivative. You finish this sentence for me. F prime equals 0 when what?
X.
When 36x minus 4x
Equals 0, right? When this whole thing equals 0. Let's do one step in our head, though. If that's all equal to 0, how would you solve for x? What's the first thing you'd probably do?
You would
Set it equal.
You would subtract the negative 4.
So move that to the other
Yeah.
side. So this, would you agree then, it's a fair statement to say our derivative is 0 when 36x equals 4x log x?
Yes.
Okay.
You would divide that, right?
Okay. You know what? We don't want to do that, though, do we?
Oh.
How come we don't want to do that?
Good.
Because we're going to have to factor, aren't we? Everybody see that? That's a bad move. That happens in math. Okay, yeah, so now how are we gonna solve that?
Well, you can take it out of 2x.
Good. We could take out, in fact, we could take out a
4.
4x. So 4x times 9 minus log x equals 0. Okay, so then, what are my zeros going to be? By the zero product property, I can set each of these equal to 0, right? So we're getting 1 at x equals 0. Is that a good one? What's wrong? I mean, it's
It's not
not in the domain, is it?
it's zero.
Right? So does everybody see that we can cross that one out because it's not in the domain? That's not even one we need to worry about. But what about this one? If I set this guy equal to 0, I'm gonna get log x equals 9.
Yeah,
Okay, how do I solve that?
gonna go E.
Yeah, good. Okay, I undo a natural log by exponentiating both sides. They're inverses, right? So they cancel each other. So then that tells us that x equals e to the 9th. So there's my one critical number of the first derivative, okay? And we can start to make our table. And really, this is, we'll do the question as it's asked here. Does it ask us to find inflection points? No. So do we really need to even find zeros of the second derivative? No. All we need to do is find the sign of the second derivative at my critical numbers, okay? Now, I want to ask you a practical question. We're going to do the question the way it's asked, but this is actually a really important question. Let's start our table here. So we're going 0 to infinity. We had a critical number at e to the 9th. And that's where we had a 0 of the first derivative. Okay, would you choose to do the second derivative test here?
No,
How come?
because you only need like two values.
Yeah, it's not worth it. It's a, yeah, I mean, maybe, it's a pretty easy derivative, but you have to do a product rule, right? So why even bother with the second derivative if it's not convenient? Because all you're looking for are relative extrema in this case. So you don't really involve the second derivative in finding relative extrema unless it's pretty easy to do, right? Now, they ask us to use the second derivative test, so we'll do it, right? But you see that we wouldn't need to. We could just pick test points around the left and the right of e to the 9th in our domain and use the first derivative test. Because, look, we already have it in factored form up here, right? There's our factored form. If I want to write, just write this in factored form, we just had 4x times 9 minus log x. It's pretty easy for me to evaluate the sign of the first derivative at test points if I've got it in factored form, right? Okay, but let's go ahead and do what they ask us to do, and we'll take the second derivative. But we want to use this form here, though, don't we? Right? So then, what's my second derivative going to be? First term is 36 minus, and then I'm going to put all this stuff in brackets because I'm subtracting the derivative of that product. So I'm going to get 4x times the derivative of log x, which is 1 over x. Plus log x times 4, right? And that's going to give me 36 minus 4 is 32 minus 4 log x. Okay? And so if I pick some values then, actually I don't pick any values, I'm just going to evaluate this at e to the 9th. We're doing the second derivative test. So if I evaluate my second derivative at e to the 9th, what am I going to get? What's the sign going to be? F double prime of e to the 9th equals 32 minus 4 times the log of e to the 9th.
So 4 times
4 times 9,
32.
right? So I don't even care what the value is, I just need to know that it's negative. And so what's that tell me about my function then? I've got a horizontal tangent. Good, and it's a sad function, right? It's concave down, and so we know that. Okay? They want to know probably the point, I'm guessing. I didn't write that part of the question down, but if they want to know the ordered pair, I just plug e to the 9th into the function. Okay? Is that, Andrew, does that answer your question?
Yep.
Okay. All right. So now, moving on, let's take a look at, we'll just warm up a little bit. So now we're into some kind of new stuff. So I want you to click all those closed and let's take a look. Let's just warm up with some, like looking at some functions, and you tell me some behavior based on the graph of the function. So this is a graph of f, not f prime. So where is f prime 0, positive, and negative? So we're looking at the first derivative. And let's just assume, well, so where is it positive and negative and 0?
It's 0 around 1. And
Okay, so these are inconvenient points, aren't they?
Yeah.
But there's a point right there where I get a horizontal tangent,
And it's that one.
and that's another inconvenient point. But those are gonna be the places where f prime is equal to 0, right?
Yes.
Okay. And then in between, so if we were like to divide this up vertically, those are gonna be the boundaries of my increasing, decreasing behavior, right?
Yeah.
So where is it gonna be increasing? Okay, yeah, over here, right?
Yeah.
So we get increasing, decreasing, increasing, right? Okay, good. So now what about concavity? Second derivative, right? Where's the second derivative equal to 0? That's a little bit trickier, but I want you to think about this.
It's 0, 2.
About 2. Okay, how come? Andrew, how come?
It's like it's the fourth. It's where they're switching out.
Okay, okay. You can't see, it's different, isn't it? You can't see where, I mean, I can see that the first derivative is 0 at that point right there and at that point right there because I can see horizontal tangents. I can pinpoint, just by the shape of the curve, I can pinpoint those exact places in there. It's a pretty clear relationship. With concavity, you can't really see where you have 0 concavity. It doesn't show up like a horizontal tangent. But we know it's a 0 because it's a transition from negative concavity to positive concavity, right? And it's a place where, how do I know that it's 0? Because it's a place where the tangent line exists and we switch concavities, right? Now that's different from something like this. And I want to make this very clear. So what if I had a similar function that was doing like this? So it was concave up, and then all of a sudden now it's going to be concave down.
No tangent line exists.
You see the difference? So this is not a place where you're going to have 0, second derivative equal to 0, because the tangent line doesn't exist there, right? The derivative doesn't exist, and so the second derivative can't exist, right? Okay, but here we do, right? here's a place where we're changing concavity, and we do have a tangent line, and so then this is gonna be the boundary between negative concavity and positive concavity. Okay, good? Yes, sir.
Would it just be the halfway point between the two, like the maximum?
Not necessarily. It is in this case because we've got some higher symmetry in this function. It's a cubic, and it looks like the peak and the trough are symmetrical. They wouldn't have to be, right? I mean, you could have something, like what if I drew something like this? What if it went like that or something, right? Or the radius of curvature of those two parts of the function were different. Then it wouldn't have to be a linear relationship. Okay, good question. All right, what about these? True or false? The zeros of f prime are -3, 1, and 4. So the local extrema are located at these points. True or false?
True.
Okay, read it again. It's false. I'll tell you it's false, but I want you to tell me why. I mean, this is a matter of semantics too, because you might be interpreting this as saying the only possible locations for local extrema or relative extrema are at those places. And that's, say it again. But even then, I could see a way that you can come up with a false statement, a converse statement. If you can come up with one statement that is untrue, then the statement is false, right? Okay, so what if we interpreted this to say that those are the only possible places where you could find extrema? What's wrong with that? Where else could you potentially find extrema? Where it's undefined, right? Okay, but that's, I don't think that's really the intent of the question, but it's still wrong. Does it guarantee that you're going to get extrema at all those places?
No, just
No.
you're gonna get horizontal.
Yeah, just a horizontal tangent line. It doesn't necessarily have to be an extrema, right? It could be an inflection point or something. So I'd say, there's a little bit of ambiguity there, but I'd say that's false. Okay. Now what about this one? The zeros of the second derivative are -2 and 4. So the inflection points, those are definitely inflection points. Raise your hands. True or false? Raise your hand. Taylor, what do you think? Does that mean it has to be true? Is it possible that you could have zeros of the second derivative that are places that are not inflection points? Okay, and you might remember, it's been a few days, but we looked at one like that. What if we look at something like, for example, x to the 4th? If we look at a graph of f of x equals x to the 4th. What's that look like? So x to the 4th just looks like, kind of like that, right? It's just like a little bit squared off parabola, right? So when we do our table, the second derivative, first derivative was 4x cubed, second derivative was 12x squared. We get a 0 of the second derivative at 0, but clearly that's not an inflection point, right? It ends up being a minimum. Okay, so it's possible that you could get false alarms with that too. Just because there's zeros of the second derivative does not guarantee they're inflection points. You still have to check the f double prime row in your table to see if it's a point of transition of concavity, right? So that's also false. The zeros of the denominator of f are -3 and 4, so the function has vertical asymptotes at those points. Think about that one. Can you come up with just one example where -3 and or 4 are zeros of the denominator, but they're not vertical asymptotes? Brandon, can you think of any?
Well, if they're in the denominator and those are the zeros, then you can't divide by 0.
You're right.
So then it's not true. I mean, it is true.
It seems like,
It-
That-
Can there be
that's-
a whole instead of an aspect?
okay, but they could be shared zeros, right? Right, so what if we had something like this? What if we had f of x equals x squared over x? X is a 0 of the denominator, right? But it's also a 0 of the numerator. Now, if we simplify this, if I were to take this limit, right, remember this goes back to our limit stuff. If I take the limit of f of x as x approaches 0, well, what do we get? If I take the limit, I could just reduce that, right? I could just reduce that function and write it as a simpler function. We're taking the limit of the function x as x approaches 0, and we get the answer 0, right? And if we look at a graph of this function, it's going to look like, remember what that would look like? It's going to look like a graph of f of x equals x, except I'm just going to have a hole, 0.00. Okay, so once again, that is false.
Why didn't you just put false statements?
Yeah, they're all false, aren't they?
Yeah.
Is anything
never true.
Okay, so now,
Is anything like
So those are
true?
okay.
so now, I tell you what, should we start another little Friday football fun competition?
We've never done Friday football.
We've never done Friday football
I don't
fun?
even know what that is.
Oh, man, we gotta do Friday football.
You didn't tell me never-
It's no longer football season, so it'll probably end up being, like, this could be for the, we'll just kind of start one and keep going, it'll be for
Who do
the
you think will
first.
win the Super Bowl 2020?